Hi, everybody. It's nice to be here. Uh, and I'm going to talk today about what has been dubbed the Fulton Gap. Um, this is the gap in the radius distribution of small planets that we identified back in 2017. And I'm going to talk a little bit about the observations and what we gained from those observations and some plausible explanations for how we think this feature in the radius distribution might be formed. I'm going to start off in a bit of an unusual way, but I like to run my talks like this. So we're going to start with the key takeaways first. These are the things that I hope that you'll get out of this talk by the end. And we're going to keep coming back to these as we go through each of the subtopics and try to understand and try to convince you of each of these bullet points. To start, like any exoplanet demographics talk, we have to talk about where the field has come over the past 30 years, such that it allows us to do demographics on exoplanets. Of course, these are the planets that were known in 1987. I'm plotting radius on the y-axis and orbital distance from the host star on the x-axis there. All we knew about at that time were our solar system planets. We had 9 of them at that time. And as the years went on, we started to detect planets. Starting in about 1995, we started to detect planets orbiting other stars. And then in 2008 to 2012, when the Kepler mission was in its heyday, we really saw this explosion of exoplanet detections. Now you'll notice that the exoplanet detections are somewhat concentrated in different regions on this plot. Now there's certain classes of exoplanets that we can identify here already. Up in the upper left here are the hot Jupiters. These were the first exoplanets discovered, and they're Jupiter-sized and mass, orbiting very close to their host star with orbital periods of only a few days. These are the easiest planets to detect, and they were the first ones to detect as a result. In the lower left here, we have the hot Earths. These are small, likely rocky planets with radii about 1 to 1.5 times the size of Earth. And these ones are very difficult to detect, so we can only detect the ones that are very close to their host stars and transit very frequently. Some of these have orbital periods of less than a day. Out in the outer regions over here on the right side of the plot, we have some directly imaged planets. These are, again, very massive planets orbiting very far away from their host stars at tens to hundreds of AU. But you've probably noticed where the bulk of the planet population lies, and that's right here in the lower center part of the plot. The majority of these planets in this region were discovered by the Kepler Space Telescope. And these planets were pretty interesting from the start, since we don't have an example of such a planet in our own solar system. These things are between the size of Earth and Neptune, and we don't really have a good idea of what those might look like. And so there's a few ways we could go about trying to understand what they look like. The two possibilities are either these things are more like scaled up versions of Earth with a large rocky surface and a thin, little to no atmosphere on top of that, or they have a smaller rocky core and they're surrounded by a thick envelope of volatiles, hydrogen, helium, or water, that makes their radius puff up a bit. There's several different routes we can take to try to determine which of these two scenarios is most common. We could try to understand the formation of these planets. We could input the physics that we know into models and try to simulate what comes out of these models, what kind of planets are produced. We could look at their atmospheres directly, since that's a key part of the question. We want to understand if these atmospheres are thick or thin, whether they have water in them. Eventually, we want to know if they have biosignatures in them as well. For this talk, I'm going to focus on the bulk properties aspect. So simply by knowing the radius, mass, and density of these planets, we can determine if they're rocky or gaseous. If they're below a certain mean density, they have to have some volatiles in them in order to make that density physically possible. Of course, the Kepler mission, since most of these were discovered by the Kepler mission, we have the radii for these planets to quite good precision. Of course, the depth of the transit is proportional to the radius of the planet over the radius of the star squared, which is about 80 parts per million for Earth, which is very small, but we could detect signals this small using the Kepler Space Telescope. Now, another complication we have to deal with when studying exoplanet demographics, as you've probably heard in other talks this week, is that we have to correct for the underlying completeness of our survey such that we can understand the planet occurrence rates and not simply see and not be affected by limited detectability of certain types of planets. So planets can be missed in a survey for several different reasons. Two of them are that it either is not aligned with the star, the geometry is just wrong so that it never transits, or the planet could be too small or the star too active such that the signal and noise just doesn't allow us to detect a planet of that size. So in order to correct for the lack of detectability in some parts of this plot, we have to correct each detection by the probability that it would be detected. So instead of simply counting planets up in order to make distributions, we count each planet and give it a weight given by this WI term here. That's 1 over the probability of detection times the probability of transit. The probability of transit is just a geometric term to say how likely it is that that planet would pass in front of its host star as observed from Earth. The probability of detection is a little bit more complicated. We have to determine that empirically by injecting transit-like signals into the light curves and seeing if our pipeline can recover it. Once we have these weights, then the number of planets per star from the underlying distribution of planets then in a given bin is just 1 over the number of stars observed in the survey times the sum of those weights. So if a given planet is very difficult to detect other planets like that, it essentially gets a boost saying that, well, if we detected one of these very difficult planets to detect, there must be a lot of other ones like it that we're likely missing. Now, of course, measuring the occurrence rate of planets was a primary goal of the Kepler mission. One of the main goals was to determine the frequency of Earth-like planets orbiting solar-type stars. The early occurrence rate results showed us that smaller planets are incredibly common, much more common than their larger counterparts and more common than we may have expected before Kepler. These early occurrence rate studies showed us that these small planets are not only common, but incredibly diverse. There are cases of extremely low density puffy planets and very high density massive planets. However, one common limitation that these early studies shared was that we only knew the stellar radii to about 40% precision. All we had was broadband photometry for the majority of these stars, so we couldn't pin down those stellar radii very well. And you might recall that the planet radii that we're trying to get depend on our measurement of the stellar radii, since we're looking at the transit depth here. So that essentially smeared out any features in the radius distribution due to those uncertainties in the radii. These early studies could have broken up their bins on these plots narrower, but they simply would have been seeing additional noise and they wouldn't have been able to pull out any physical properties of the distribution. So this motivated the California Kepler survey, which is a large Keck program that operated mostly through 2011 through 2015. In all, we collected high-res optical spectra of 1,305 stars hosting 2,025 planet candidates. We observed stars as part of this project for several different reasons. There was a magnitude limited sample, which is what I'm going to be focusing on since we kind of understand the selection effects there the best. We observed all multis, ultra short period planets, and anything that potentially could have a planet in the habitable zone as well. So here are the uncertainties before and after the California Kepler survey. In effective temperature, the photometric best we could do before that, uncertainties are about 150 Kelvin. With the spectroscopic parameters from CKS, we were able to push that down to 60 Kelvin. You can see similarly impressive gains in surface gravity and stellar mass, but the one we really cared about was the stellar radius, where we pushed the stellar radius uncertainty down from about 40% all the way down to about 10%. And with that, I think I've shown you how important it is to have precise stellar characterization if you want to precisely characterize the planet population underlying that. We're gonna need spectra or astroseismology, something that gives us very precise planet radii. Fortunately, Gaia helps out with this a little bit, and I'll get into that in a bit. But what did we find when we improved our planet radii? Well, here was what the distribution of planet sizes looked like from Kepler before our update. You can again see that the small planets are very common, but note the typical uncertainty there in the upper right. If you compare that to the distribution after the California Kepler survey, all of a sudden you see this very interesting feature pop out in that radius distribution at about 1.5 times the size of Earth. It appears that these small planets are not equally as common. They tend to prefer to come in one of two sizes. They're either about 1.2 times the size of Earth, it could be a little bit smaller, or they're about 2.5 times the size of Earth. Now, we think this gap in the radius distribution actually separates the population of small planets into two subclasses. I'm going to call them super Earths, the ones to the left of the gap, which likely have little to no atmosphere to speak of. And then ones to the right of that gap, I'm going to call sub-Neptunes, which have to have some volatile atmosphere. Now, the presence of this gap is not the only line of evidence that supports our idea that this is a dividing line between these two types of planets. In fact, if you just look at the density of these planets, which is now I'm plotting that on the right-hand axis here, and these individual points, you'll see that there's a ton of scatter because it's a difficult measurement to make. But in general, the planets to the left of that dividing line tend to be higher density on average, and those to the right tend to be lower density on average. The K2 mission helped out greatly because it detected more planets around brighter stars, and we could get higher precision in our masses. And this became even more clear that there's these two populations, not only in radius, but they also bifurcate in density, which is a nice confirmation of that split in these subclasses of planets. Also, if you look at the distribution of ultra short period planets, those hot Earths that I mentioned earlier, these things are so close to their host stars that they couldn't have any atmosphere to speak of. It would be evaporated away very quickly. So we know that these are bare rocky cores essentially. Now, the distribution of planet sizes for those planets falls off rapidly as you go to larger sizes. And there's essentially none larger than about 1.7 times the radius of Earth. And this distribution corresponds quite nicely with the left side of the distribution, those planets to the left of the gap in the full radius distribution. Okay, so I hope now I've convinced you that small planets come in two sizes. They don't have an equal probability of being any size between 1 and 4 Earth radii. They seem to prefer to be about 1.5 or about 2.5 Earth radii. Now, in our original CKS survey in 2017, we simply had stellar radii that were derived from stellar spectroscopy. At that time, we tried to fit the distribution and get a handle of the underlying distribution in the absence of any remaining stellar radius uncertainties. Our prediction at the time was that this gap could actually be sharper and that planets in that gap are even more rare than we could make out at this time because the uncertainties were still a significant factor in determining the underlying radius distribution. So that motivated us to get prepped for the release of the Gaia Data Release 2. This gave parallax and proper motion for over 1 billion stars in the sky, and most importantly, most of the Kepler field stars. So we knew when this would come out This would give us a big advantage and another way to improve the stellar radius precision. And we were ready to go at 4 a.m. right when this released. So how does the Gaia parallax actually help us? Well, if we have spectroscopy, which of course we already did from the California Kepler survey, then you can simply use the Stefan-Boltzmann law in order to derive the stellar radius. So if you look at Stefan-Boltzmann's law, that's up on the top line there, and then you can rearrange it to solve for R star there. Now you see that it's a function of T effective squared, or 1 over T effective squared. So it's a rather strong function of T effective. Fortunately, we have good temperatures from our spectroscopy. That's one of the easiest things it is to pull out of the high resolution spectroscopy. And so now we just need the bolometric luminosity. Well, this can be translated into a bolometric magnitude, and that can be broken down into several terms. First is the single apparent magnitude, which we can get from a variety of photometric surveys. You need the extinction in that magnitude band, and if you choose your magnitude to be, say, in the near infrared, that extinction to the Kepler field can be essentially negligible. You need the distance modulus, and that's where the parallax comes in. And then you need a bolometric correction, which we can get a good handle on from stellar isochrone models. So we went through this exercise again, improving the radii, and this is what happened. So the first CKS result, I mentioned we had a median stellar radius uncertainty of about 11% there, and that's the distribution in light gray. After the Gaia data release 2, we were able to push that down to a median of 2% uncertainties on the stellar radius uncertainties. As far as the planet radius uncertainties, we were able to go from 13% median down to about 5% median. So we had similarly impressive precision improvements between the previous CKS result and the CKS Gaia result. And so we are expecting equally mind-blowing results to come out of this as well. So here's what the radius distribution looked like before Gaia, and this is what it looked like after Gaia. And to maybe our disappointment, the distribution ended up looking almost exactly the same. So let's investigate what's going on here. Well, if you look at the distribution in 2 dimensions, where now I'm plotting planet size on the y-axis and stellar light intensity relative to Earth on the x-axis, the contours there are the underlying completeness corrected occurrence of the planets, and then the dots are the individual planet detections. Note the typical uncertainty labeled in the upper left there. So the original CKS work from 2017 is on the left, and you see the contours. You can see a gap, but the contours are quite blurry. On the right is the post-Gaia revisit, and you can see that the 2 populations are able to be spread apart much cleaner in this 2-dimensional space. Now that I've shown you this 2-dimensional version of this plot, I wanted to kind of describe some of the main features that we see here. So first of all, there's this noticeable dearth of planets in the upper left. This is known as the photoevaporation desert, and it was something that was known before our 2017 study. It's hard for planets that are very close to their host stars to hold on to any atmosphere regardless of their size. I mentioned this for the hot Earths, but up to Neptune-sized planets would also get stripped if they're that close to their host star, if there was rocky cores that big. And then, of course, you see the radius gap, which splits these 2 populations there. On the lower right is an area where I've shaded to mark an area of low completeness. The fall off in occurrence that you see in this region is likely not to be trusted. It's probably an artifact of having very low completeness there. So since this cleaned up the distribution a little bit, we were able to pull out a few more details of the radius distribution that we couldn't do the first time. One is we determined that the gap is really not empty, at least not in these planes. We determined this by setting up a simple toy model, simulating the uncertainties in the stellar radii and the planet radii. And we would make different assumptions about the relative occurrence of planets inside these little boxes and outside those boxes, add the uncertainties, simulate them through, and see what they would look like compared to our real detections. And clearly something with a distribution, an intrinsic distribution width to these two populations of about 60% works much better than smaller widths. So that means that there are really planets that scatter into this gap, and it's not completely devoid of planets. Now, this may seem in contrast to a result that came out not too long after our original work by Van Allen et al., who had an astroseismic sample of stars where they had even better radius precision than our post-Gaia update. And he found that there were 0 planets in the gap in that sample. Now, I think that there's several things going on to explain that. One is that it was a relatively small sample, so the probabilities of something getting scattered in there are a little bit less. And second, it was a relatively narrow range in stellar mass. And another thing that we found as part of the Gaia update is that when you break up the sample by stellar mass, these two populations split apart even farther. What we found is that the photoevaporation desert in the upper left does seem to extend to lower fluxes for more massive stars. So if you look at the plot on the right here, this is for the sample of stars that are most massive in our overall sample. And you see that the area on the upper left, known as the photoevaporation desert, is much more populated in that plot compared to the far left plot. We're also noticing that if you look at the population of planets on either side of the gap, you might notice that the peak location shifts upward as you go towards more massive stars. So the planets orbiting more massive stars are on average larger and hotter than the planets orbiting low mass stars. Now, we broke up our sample by stellar mass, and we noted a caveat that stellar mass is correlated with both metallicity and age. Still, we wanted to see how the planets evolved or changed when they're orbiting stars of different masses. Another way to look at this is simply by plotting planet size as a function of stellar mass. And in this plane, you do indeed see that the gap between these two populations is not totally flat. It has a little slope to it, and so do the peak locations of the populations on either side as well. Now, we also broke this up into a few different bins, and we tried to look at the average planet properties in these bins to get more of a quantitative handle on the significance of this trend. So on the right, I'm showing a breakdown of the average planet size on the top row, average insolation flux of those planets in the middle row, and then average orbital period on the bottom row. So on the top one, if you look at average planet size as a function of average stellar mass, you see indeed that the planets orbiting more massive stars tend to be larger. In the middle row, you see that also the average insolation flux goes up for these planets as you go to more massive stars. So they're hotter as well. Now, you don't necessarily see such a clear trend in orbital period, however. So as I mentioned, we broke our sample up by stellar mass. But there's a caveat that mass, metallicity, and age are all correlated with each other for stars within a same galactic population. So right after our IPAC-NExScI paper came out, there were several other papers that went back and forth on this. 2 of them were Wu 2018. They agreed with us that it was essentially a mass effect and not metallicity. But then Owen and Murray Clay published a result about the same time saying it looks like it's a metallicity effect and not mass. Whereas we said it was mass, but argued it could be metallicity or age at the time. I think it's difficult to determine which of these things are at play, and this is definitely work that should be pursued further. Okay, so I think that covers key takeaway number 3, that properties of the planets orbiting those stars depend on the properties of those stars. Whether they depend on the mass of the stars, metallicity of the stars, age of the star, or some combination of 2 or 3 of those is not yet clear, and definitely an area that needs to be focused on. Okay, so now that I've covered most of the observational stuff, I wanted to get into some plausible explanations for how such a gap might arise in the exoplanet radius distribution. And the first one we jumped to was the idea of photoevaporation. This was a theory that actually pre-existed the 2017 California Kepler survey work. There was a prediction that showed that in the presence of highly evaporating extreme ultraviolet photons, you would expect a gap to form in the radius distribution, just like we observed. The way this works is essentially you look at this plot on the right, which is mass loss timescale as a function of envelope mass fraction. Now, this timescale, you'll notice, peaks at an envelope mass fraction of a few percent, 2 to 3%. That is the envelope mass fraction or amount of atmosphere that is the most stable to evaporation. Now, since the period of time in which a young star emits most of the photons that do the evaporating of the atmosphere is only about 100 million years. They're really active for the first 100 million years of their life, and they start to settle down and produce a lot less of that XUV photons. So anything that is below that dashed line here at 100 million years would essentially be stable to evaporation and be able to outlive that. Now, I'll explain this plot a little bit more detail in a cartoon example on the next few slides. So don't worry if you don't understand it quite yet. But what this says, the prediction was that most sub-Neptunes are likely 2 to 3% hydrogen helium by mass. And those have the longest mass loss timescales, and it tends to herd planets into two typical sizes. Okay, so now let's go through a cartoon example of how this actually works. Let's start with a planet that has a 20% hydrogen helium by mass envelope around a 3 Earth mass core. The core has an Earth-like composition of mix of rocks and iron. Such a planet would have a radius initially of about 4 Earth radii. So in the radius distribution plot, it falls right there. And in the envelope mass loss timescale plot, it falls right there. This big puffy atmosphere has a large cross section. It's going to evaporate a lot, or it's going to absorb a lot of XUV photons. So although it started on that part of the plot, it's going to quickly evolve to the left. It's going to shrink down until it reaches a sort of equilibrium point where the radius has shrunk enough that its cross-sectional area is smaller and it's absorbing less photons in that atmosphere. The star has likely quieted down a lot, so there's less XUV photons to do the evaporating, but yet the mass of that core is high enough, and the mass of that atmosphere on top of it is enough to retain the rest of that atmosphere throughout the lifetime of the star. So it will end up at that peak of 2.5 Earth radii there. Now, if you have a planet that starts at a slightly smaller radius, say 1.8 times the size of Earth, you would have something like a 0.3% hydrogen helium envelope. Now, since that starts to the left of the peak in the envelope mass fraction function here, that atmosphere is quickly going to get stripped away completely. There's just not enough of it to outlive the period of time in the star's life when it's extremely active and emitting these XUV photons. So it's going to get completely stripped down to just the bare rocky core, and it's going to end up on the left population of planets here, down about 1.2 times the size of Earth. Let's look at this in some more detail as a population of planets. So if you were to create a simulated population of planets with an initially sort of random distribution of envelope mass fractions, and then evolve that through time under the influence of photoevaporation, you're going to tend to see these planets herded into these two groups. So I'm going to show two examples. I have this population of planets in the darker blue points there, and then I have a single planet with the big light blue atmosphere and a rocky core on top of that to illustrate what's happening to the planets around that in that area. So it initially starts out rather large, about 5.5 times the size of Earth. As time goes on, it shrinks down. But notice on the right here, the planet's size is asymptotically approaching about 2.5 times the size of Earth. the evaporating photons are slowing down, and that cross-sectional area is shrinking, and it's reaching this sweet spot of 2.5 times the size of Earth where it wants to live and stay for the rest of the star's life. Now, in the other case, if you have a planet that starts slightly smaller or slightly less atmosphere, you're going to have a situation where it evaporates down through that equilibrium zone over that peak and quickly falls into the population of bare rocky cores at the bottom. So if you look at the population of observed planets relative to the population that you would simulate, the agreement is quite amazing, I would say. It looks like the model was pulled out of a fit for our observations, when in fact it wasn't at all. Since the agreement is so good, we're actually able to pull out some rather profound implications about the formation of planets. First, Earth density cores are what's dominating the population here. All of the cores underlying whatever atmospheres they have to essentially have Earth density. That means they're relatively water poor, something like less than 20% by mass water. So they're not ice worlds, nor are they solid balls of iron. They need to have some sort of mix of silicates and iron in order to match the observations. That peak, the location of the gap would shift towards larger or smaller radii, depending on the density of these cores. So the location of the gap tells us the density of these cores. Since these cores are sort of water poor, that indicates that large-scale migration, at least from well beyond the ice line, is probably uncommon after the first 100 million years. Now, photoevaporation is not the only explanation for the gap. Of course, there are a lot. You can get this by pebble accretion, giant impacts, outgassing of the gases trapped in the mantle can produce a few percent by mass envelope. But perhaps the most comparable competing theory to photoevaporation is the core heating or core powered mass loss idea. And this essentially reproduces the observation equally as well as the photoevaporation models. It's very difficult to distinguish the two. And this is nicely illustrated in a recent paper by Rodriguez et al. 2021, in which they directly compared the predictions from these two models. So what I'm showing here is a plot from that paper. On the left are the contours are the underlying occurrence distribution as measured from our CKS work. Then the individual points are simulated planets that have gone through their either photoevaporation or core powered mass loss models. And as you see, the contours line up quite well with these simulated planets in both cases. And there's really no distinguishing these two, at least with the precisions and numbers that we have here. The reason for this is if you look at that mass loss timescale plot, which is the same as what I'm showing here, those two curves look quite similar. They both have a peak at around a few percent by mass envelopes, and they fall off on either side. And that leads us to the same situation where either can cause a gap and a bifurcation in the planet population here. One of the best ways to distinguish between these two models, it appears, is to look at the planet size as a function of stellar mass. There's a big difference here. And if you were to, this is now looking only at a very narrow slice in stellar insolation flux. So you have to look at a fixed insolation flux. You're going to see that the location of the gap, or sort of equivalently, the largest size of the bottom population of planets, the rocky population of planets, has a slope to it in the photoevaporation case, where essentially very close to the host star, you can evaporate away planets that had larger cores to start with, so that that maximum size of a rocky core is larger as you get very close to these stars. That's because the Low mass stars actually have a higher XUV to bolometric flux ratio. They're producing more XUV flux. So at a given incident flux, which is a bolometric term, you're going to see that the low mass stars do more evaporating. That's not really the case with with core powered mass loss. And you see that this line is relatively flat across this stellar mass regime in that case. This is potentially one way to distinguish between these two different these mechanisms. However, they determined that you're going to need a survey of something like 5,000 planet detections with 5% precision on the radius in order to do that. And we simply don't have that yet. So those are some differences between those two ideas, but what I wanted to focus on is the common threads. Basically, it's quite simple. You have to form rocky planets, out of rocky building blocks. They have to be about Earth-like density, so you're not forming them out of solid gas, solid ice, or solid iron. Some mix of those materials will form rocky cores. You have to form these rocky cores fast enough such that there's still gas in that disk, and they can accrete and gather that gas around them to form an envelope. Now, if you add heat to those that started with a large envelope will get herded down into the class of mini Neptunes, where you have a few percent by mass hydrogen and helium. Those that started with anything less than that threshold are going to get completely evaporated away and turn into these bare, rocky super Earths. Okay, so I hope that last section helped to convince you that there's probably multiple pathways that can equally reproduce the observations. But what you really need in order to produce this, in any theory, it's a population of rocky planets with rocky cores, some volatile envelope that came from somewhere, some heat input into that atmosphere, and that will create your dichotomy. So in summary, I think I'll leave up my summary slide here and leave the rest of the time for questions. Thank you for your attention.